Hello students, and welcome to the new lecture about bond energy. Bond energy, or heat of the bond, right, enthalpy, is the heat change required, or the enthalpy change required to break a particular bond in 1 mole of the gaseous molecule. So how much energy is it going to take to break that covalent bond in 1 mole of a gaseous molecule? It's measuring the stability of the bond or the molecule, because the harder it is to break the bond, the more stable the molecule. So a strong bond will take a lot of energy to break, and a weaker bond will take definitely less energy to break. So here is an example. If I have a covalent bond between 2 hydrogen atoms in a hydrogen molecule, breaking it means breaking it back to 2 hydrogen atoms. That heat of energy, the amount of energy that I will put, and it's endothermic, positive sign, is 436.4 kilojoule per mole. So every mole of a hydrogen molecule, breaking that bond will cost 436.4 kilojoule. Now, breaking a bond between hydrogen and chlorine in a hydrogen chloride molecule will cost 431.9 kilojoule per mole. So kind of something very comparable. Oxygen molecule, remember that oxygen has a double bond. Breaking that bond will cost even more energy, because double covalent bonds, you're breaking 2 bonds, so naturally you're going to have to spend more energy breaking the double bond. Nitrogen molecule has a triple bond, so you can see that delta H is even higher and higher, because now you're breaking 3 covalent bonds. Generally speaking, the single bond is lower heat, the bond energy of a single bond is lower than a double bond, lower than triple bond. Now, in water, we have 2 covalent bonds between hydrogens and oxygens. So breaking the first one will cost 502 kilojoule, and breaking the second one will cost 427. So in this case, since there are 2 bonds in a molecule, we average it out, and we say that on average, every oxygen-hydrogen covalent bond in water costs 464 kilojoule per mole. Values are always our average, since bond energy changes with environment. So here is what you normally will find. You will find a table, and I want you to pay attention. In this table, they will list all single bonds and how much energy does it take to break that bond. And you also, at the bottom side, you can see how much does it take to bring certain multiple bonds. Pay attention to this one in case you ever see it again. Oxygen here, they really mean the oxygen molecule, right? Which is, as you guys know, oxygen double bond. Okay, and this is how much it costs. Now remember, bond energy by definition is the amount of energy needed to break the bond. So this is why all these values are positive. And I want you to keep in mind, if breaking the bond is endothermic, making the bond should be exothermic, okay? If making the bonds are endothermic, making them will be exothermic, because it's the opposite. Opposite of breaking a bond is making it. Now, that also reflects on the bond length. So the more bonds are between 2 atoms, the stronger the bond and the shorter the bond is, because the 2 nuclei become closer to each other. So if you look here, you will see that let's go back. You will see that a nitrogen triple bond is shorter than a nitrogen double bond, which is shorter than a nitrogen single bond. Same here. Carbon-carbon single bond, longer than carbon-carbon double bond, longer than carbon-carbon triple bond. So when it comes to bond length, the single bond is longer than a double bond, which is longer than triple bond. In another way also, the shorter the bond, the stronger the bond. Okay, now look at the energy and correlate that strong bonds are short bonds and are more stable. As the number of bonds increases, the bond grows shorter and stronger is another way to also make sense of these numbers. Now what we're going to do right now is we're going to use bond energy to calculate delta H for a reaction. Remember in the thermodynamics chapter, we learned 3 different ways to calculate delta H. We learned how to calculate it using calorimetry, heat gained equal negative heat lost. We also learned how to calculate it via Hess's law and via standard heat of formation. Now we're going to learn how to calculate it using the bond energy table. When we make reactions, all the old bonds in the reactants have to break, and all the bonds in the products, the new products, right, has to be made. So there are bonds that are breaking, which means you put energy, endothermic, and there are bonds that are formed, which means they're going to release energy and going to be exothermic. So heat of energy, or delta H, is okay, how much energy I put and how much energy was released. Now this negative sign here, because I can only measure the energy, guys, via the table. The table can only tell me how much does it take to break. So I put this negative sign because the energy here of the bond released, the table will give them a positive value because the table only shows how the energy to break them. So I put that negative here to make them exothermic. So the way I'm going to calculate that, it's if I go to the table, again, what does the table have? What it takes to break? Which bonds I am breaking? Reactants. So if I sum the bond energy of reactants, and then I also sum the bond energy of the products. However, products, the bonds are being made. That's why I put the negative sign before them, right? Because products, the bonds are being formed, being made, not being broken. I don't have another table that reverse the sign because I want to look at making the bond. They just assume that I understand. If they give me what it takes to break the bond, I reverse the sign, and this is how much energy comes out when the bond is formed. Okay? So now, let's look at what we have. Calculate the enthalpy change for the reaction when hydrogen reacts with a fluorine gas to give me hydrogen fluoride. Here is what I have to do. First thing first, if you want to know what bonds you're breaking and what bonds you're forming, you do have to know how to draw Lewis structure, because how else you would know what covalent bonds you're breaking or making. So for this question, hydrogen has this Lewis structure. Fluorine has a single bond, this Lewis structure. And this is the product Lewis structure. Now what I do, I make 2 columns. Here I'm going to say bonds of reactants, and here bonds of products. What bond of a reactant do I have? I have 1 hydrogen, single bond. I go to the table and I try to find it and spot that bond. And when I find it, it is 436. I also have 1 fluorine single bond. And if I go find it, it will be 155. That's it. For products, I have 2 times hydrogen fluoride. So that will be 2 times, and here is the hydrogen fluoride, 567. So now what I do the math. So this will be for the reactants. and this will be for the products. Okay, now that I have this, I'm ready to calculate delta H. Delta H will be the bond energy, the sum of bond energy of reactant, because I break the reactant, so I'm going to keep them positive, minus the sum of bond energy of products. I am making the products, so I put the sign in front of that. Okay, so now it will be 591 minus 634. You do the math, and the answer will be, sorry, I made a mistake earlier. The sum here is 1134. So now when I do the math, it's 591 minus 1134. That is negative 543 kilojoule per mole, which is delta H for the reaction they wanted me to calculate. Let's look at another example. Here is another example. Calculate the enthalpy change for hydrogen gas reacting with ethene gas to give me ethane gas. So one more time, bond energy table is provided. I'm going to have to use it to calculate delta H. The first step is to draw Lewis structure. If I am following the rules of Lewis structure as explained in the previous lecture, then hydrogen reacting with, this is the Lewis structure of ethene, to give me ethane. So next I'm going to have my two columns here, and I'm going to say, okay, bonds of reactants, and then here bonds of products. For bonds of the reactant, I have one hydrogen single bond, and that is 436 kilojoule. Then I have 4 carbon hydrogen single bond, so this is 4 times. I'm going to have to find this bond, which is the carbon hydrogen single bond, 413. I also have one carbon-carbon double bond, so I'm going to have to go and find that as well, which is right here. So I have one carbon-carbon double bond, and that is 614. Now for the product, let's see what we have. We have 1, 2, 3, 4, 5, 6. So I have 6 carbon hydrogen bond. So this is 6 times 4, 13. And I have one carbon-carbon single bond, and that is 348. Now what I'm going to do, I'm going to do the math. Now what we had the mass here, so we're going to go delta H equal the sum of bond energy for reactant minus the sum of the bond energy of the product, because a product I have to put a negative in front of them because they are made, and I'm going to say 2,702 minus 2,826, and the answer will be negative 124 kilojoule per mole. So this is how I use bond energy to calculate delta H. I want you to pay attention that in these equations, it's important that your equation is balanced, and also you know how to draw the Lewis structure. So that's it for this topic, and I will see you in the next chapter.